Now we are going to discuss uh, statistical mechanics. Here we are going to find the average energy of the system by using the probability and the partition function. Now let us consider a canonical example. Now here this system is divided into so many cells, and the cell is one cell is having the N1 is the number of particles, where the particle is having energy E1. The another cell is having a number of particles N2, and the energy of the particle is E2. N3 is the number of particles in cell 3, and E3 is the energy of the particle in the cell E3, and so on. Let us consider a particular cell, say S cell, and Ns is the number of particles in the S cell, and E suffix S is the energy corresponding to the particle in the S cell, and let Ps, we can consider P suffix S is the probability of occupation of energy level Es at temperature T. Now in this canonical example, each cell is separated by a conducting walls, so that the temperature remains constant, because one cell is having higher temperature, another is having lower temperature. Since it is a conducting wall, so there is a transfer of temperature, transfer of heat, so that the temperature of all the cells remain constant. So the temperature, so the exchange of energy between systems, so that it gets the common temperature T. Now here Ps is the probability of occupation of energy level Es at temperature T. So if you take the sum over all the probabilities, sum over S, the total probability must be 1, and the average energy or the mean energy of the system is defined by sum over Es Ps for all the cell S. So that is your mean energy. You can represent by a symbol U, the expectation value of E, or you can use U also. This is the mean energy of the system. Now since summation over Ps is equal to 1, if we take 1 on the other side, this is the equation, summation over S Ps minus 1 is equal to 0, and if you from the second equation, summation over S Es Ps minus U, this is equal to 0. So you have two equations. This is equation 1, and equation this is equation 2. Now you multiply the equation 1 with a Lagrange multiplier lambda 1, and you multiply equation 2 by Lagrange multiply lambda suffix 2, and once if you add, so if you take this equation, if you take a multiplying by lambda 1, so this is the equation 1 becomes like this, and once if you multiply, take the equation 2 and multiply by lambda 2, and you will get this equation. And once if you add the two equations, this will be lambda 1 into summation over epsilon summation over S Ps P suffix x minus 1 plus lambda 2 into summation over S of Es E suffix x P suffix x minus U. So this must be equal to 0. So this is from equation 1 and 2, you multiply lambda 1 with 1 and lambda 2 with 2 and add, you will get this equation. Now let us add the S on both sides. S is the entropy. If you take S on both sides in the above equation, so this is your S is left side you have added, and also S is you have added the right side also. In the above equation we get this one, but we already derived the equation for this entropy. S is equal to minus K sub x b Boltzmann constant summation over S Ps logarithm of Ps. We have already derived this expression. Now let us substitute these values of S in the right hand side in the left hand side of this expression. Therefore, now this x becomes S is equal to minus K suffix b summation over S Ps logarithm of Ps plus lambda 1 into summation over S Ps minus 1 plus lambda 2 into summation over S Ps minus q. So the expression for S becomes like this. So this is you put this is a function of p suffix x, because the expression contains a function of p suffix x. So this may be expressed as f of p suffix x. Now for most probable value of f of s, this is equal to, because for most probable value, if you differentiate with respect to ps, this must be 0. So you take this expression, and if you derive with respect to, you find the derivative with respect to ps, you will this expression minus. So once you find the derivative, you will get this expression minus k sub x b 1 into logarithm of ps plus ps into, if you differentiate logarithm of ps, you will get 1 by ps suffix x. So this will first term plus lambda 1. So and if you differentiate in the second term, if you differentiate ps, you will get 1. So this term becomes lambda 1 alone. And if you differentiate the third term with respect to ps, you will get lambda 2 in the e suffix x, which is equal to 0. So by simplifying, you will get this expression. So you will get this is your expression. So k suffix b logarithm of ps plus 1 is equal to lambda 1 plus lambda 2 times e suffix x. Then from this logarithm of ps plus 1 is equal to, so if we take logarithm of ps plus 1 in one side, you take the other terms to the other side, this is equal to lambda 1 divided by k suffix b plus lambda 2 divided by kb in the e suffix x. So from this logarithm of s is ps, logarithm of p suffix x is equal to lambda 1 divided by kb minus 1 plus lambda 2 divided by kb. So you will get this expression. So from this you solve the expression for ps. So find the solution. So once if we solve, so if you integrating logarithm of ps, you will get ps. So you will get the ps. The expression for ps is equal to, and this becomes e power lambda 1 divided by kb minus 1 into e power lambda 2 by kb into es. So you will get this expression. So from this your PS is equal to. So if you take the first factor as a constant, which is a capital A, e power lambda 2 divided by kb es, where a, the constant a can be written like this: exponential of lambda 1 divided by k suffix b minus 1. Now put lambda 2 by kb is equal to beta. Here T, the temperature T remains constant in the canonical exam. So actually beta is equal to 1 by kbt. Now here in that expression, PS now becomes a in the e power beta es. Now if beta is a positive value, then PS must be greater than 1, which is not allowed, because the total probability, sum over PS is maximum value, the total probability is 1, so P suffix x greater than 1 is not allowed. Therefore the only possibility is beta must be negative. So in that expression, PS is equal to a e power minus beta e suffix x. Now let us find the constant, because we have to find the constant. The constant can be determined because we know the total probability, sum over s of PS must be equal to 1. Therefore you substitute the value of PS again here. So this is equal to summation over s a e power minus beta s is equal to 1. So the constant a is equal to 1 divided by summation over s e power minus beta suffix x. So if you substitute back, you will get the expression for PS is equal to e power minus beta e suffix s whole divided by summation over s e power minus beta e suffix x. So you will get, this is the expression. Now this can be written like this: e power minus beta e suffix x divided by z. Now this z can be written like this: z is equal to summation over s e power minus beta e suffix s, so s is the sum over all the states. So this is we call as a partition function. We call this is a partition function. Z is called as a partition function. Therefore the expression for PS may be the expression like this: e power minus beta es divided by the z, where z is called as the partition function. So this is an important expression that we have to use in solving problems. Now let us discuss some problems. So if you have to, if you consider a canonical example, so the temperature must be a constant for all the cells. Now here there are two types of canonical examples. One is a non-degenerate system. In non-degenerate system, suppose let us consider levels, two levels, level 1 and 2. The level 1 is having energy E1, and the level 2 is having energy E2. Then there is one state corresponding to each energy level. The E1 is having only one state. E2 is also having the energy corresponding to the number of energy level corresponding to E2 is also 1. So the state corresponding to each level is a single. So such system we call as a non-degenerate. Now here we define P1. P1 represents the probability of occupation of the energy E1 in that level 1. P2 is the probability of occupation of the energy E2 in the level 2. So this is a non-degenerate system. So in this for a non-degenerate system, the partition function is expressed like this. So this is the expression for the partition. Z is equal to summation over s e power minus beta es. So this is non-degenerate levels. So in that non-degenerate systems, PS is also defined as e power minus beta E suffix x divided by the partition function. And the average energy or the mean energy of the system is defined by U is equal to summation over S E suffix x PS. So this is the expression. You substitute for P suffix x from the above expression. The expression for the mean energy becomes summation over S ES e power minus beta E suffix x divided by S. So this is the expression for the average energy of the system. So now let us consider a degenerate system for the canonical result. Now here we consider two levels. E1 is energy corresponding to level 1 and E2 is the energy corresponding to level 2. But here suppose let us assume that there are G1 is the number of states corresponding to energy level E1. So there are G1 number of states corresponding to the same energy level E1. So this is called as the multiplicity of the level. Multiplicity of the level is G1. Similarly, let us assume G2 is the number of states corresponding to energy level 2, because G suffix 2. So this multiplicity of the level is 2. So if you are having more states corresponding to the same energy, which is called as a degenerate system. So we consider a degenerate system, and we are considering two levels with the energy E1, E2. The multiplicity of the level 1 is G1 and multiplicity of the level 2 is G2, or we can call this the degeneracy of the level is 1 is G1, the degeneracy of the level 2 is G2. So we can call either this is the degeneracy of the level or the multiplicity of the level. Now in such a system, then the partition function may be expressed as, you have to include the GSRs here. The multiplicity of the level must be included in the expression for Z. So Z is equal to summation over S G suffix S e power minus beta ES. So there is a difference between so here you find the difference. For the non-degenerate, here there is no term with GS. For degenerate system, you have the expression GS, the multiplicity of the level must be included in that expression. So this is the expression for the partition function. Similarly, for PS, the probability of occupation of the state with the energy ES is defined as GS e power minus beta ES. So you have to include the GS here. So this is the expression for the probability corresponding to the S cell. So this is GS e power minus beta ES divided by S Z. So for the degenerate system, the term GS must be present. For the non-degenerate, GS is equal to 1. Similarly, you can find the mean energy or the average energy of the system is summation over S, GS, ES, PS. So this is GS must be here. So there are the difference between the expression for the non-degenerate and degenerate system is you have to include the degeneracy GS in that expression for Z, PS and U. Now using this, we can do some problems. Now let us consider a problem 1. Let n be the number of particles in which is distributed in the level but the energy is 0 and E. So this is find Z, P suffix x and E. So here this is energy E and this is one energy level is having energy 0 and another level is having energy E. So now let us find the partition function. Z is equal to summation over R S e power minus beta E suffix x. Now for you put S is equal to the first state. The first state is having energy 0, so you substitute here. And for the second state, S is equal to 2. This is a 2. For energy is E, so you have to substitute E here. So e power 0 plus e power minus beta E. So the e power 0 is 1, and this is e power minus beta E. Therefore, this is the expression for Z. Now let us find P suffix x. So this expression is e power minus beta Es divided by Z here, which is equal to e power minus beta Es divided by, if substitute for Z, Z is equal to 1 plus e power minus beta E, that we have already calculated. Now let us find, because we are having two levels, first to find the probability P1, probability of occupation of the level 1, which is P1, is given by e power minus beta. Here the energy corresponding to the first level is 0, so you substitute for 0. So E, yes, here is for first level it is 0. So e power minus beta 0 divided by 1 plus e power minus beta E, which is equal to 1 divided by e power minus beta A. So this is the expression for P1. So for the expression for P2, for Es is equal to E. So for the second level, so this is you put E suffix x is equal to E. So e power minus beta E divided by 1 plus e power minus beta E. So this is the expression P2. You can easily check, because the total probability must be 1, because we are having only two levels. So let us evaluate P1 and P2, because we already evaluated 1 and 2. So if you find a P1 plus P2, once if you add 1 by 1 plus e power minus beta E plus e power minus beta E divided by 1 plus beta E, once if you add, you will get 1. You can easily check P1 plus beta P2, that must be 1. Now let us calculate the mean energy. The mean expression for the mean energy is U is equal to summation over S ES PS. Now for first level, the energy is 0 into 1 by Z. For the second level, the energy is E into P1 is P2 we have already calculated. We substitute the value of P2, and if we simplify, you will get this is the expression. Now this is a E power minus beta E whole divided by Z. So this is the way you have to calculate the energy of the system. Now let us consider one more problem. You take the problem number 2. For a system of two bosons, this is we are considering two bosons, each of which can occupy any of the two energy levels 0 and E. The mean energy of the system at temperature T with beta is equal to 1 by kBT is given by. So 4 options are given. So in order to calculate this one, so the system is having two energy states, 0 and E, and so the partition function is Z is equal to summation over S e power minus beta E. But here the particles are bosons, so this is important. Boson, which is a spinless particle. Both particles are in the ground state. The energy is, because for bosons, the number of particles which can occupy in a particular level is, there is no constraint. Only for fermions there is a problem. You have to apply the Pauli's exclusion principle. For bosons, any number of particles can occupy in a particular state. So for the two particles can occupy in this way. This is 0 plus 0. The first particle as well as the second particle, both particles are having 0, then the energy, the total energy must be 0. So this is E1, which is a non-degenerate. And the second possibility is, if one particle is in the ground state and the another one is in the first excited state. So this is a first excited state, one is in the ground state. Here the total energy is 0. The second particle is in the first excited state, that means this is having energy E. So the total energy is E, which is the E2, the second energy level. You can say this is equal to E. This is another possibility. This is again a non-degenerate. And similarly, for the two particles, both particles are in the first excited state, this is also possible. First particle is having energy E, second particle having energy E, the total energy 2E, which is the E suffix 3, which is also degenerate, non-degenerate. So all the cases, they are non-degenerate, but the energies are E1, E2 and E3. So now let us evaluate the partition function. Now in order to calculate the partition function, this is summation over S e power minus beta Es. For the first state, E suffix x is 0, so that is E1 is 0, and therefore this is e power 0. Second case, the energy is the E, so this is e power minus beta E. And the third level, the energy is 2E, and therefore this is e power minus 2 beta E. So the Z is equal to 1 plus e power minus beta E plus e power minus 2 beta E. Now let us calculate the PS, P suffix x, the probability. So for this, this is the expression for PS. So let us find P1. P1 is equal to e power minus beta Is, is equal to 0, therefore this becomes 1. So this is 1 by Z. If you calculate beta P suffix 2, this is e power minus beta E divided by Z, because your E2 is E, and similarly you can calculate P3. This energy is 2E, therefore e power minus 2 beta E by Z. So you have calculated P1, P2, P3. Then the average energy now can be evaluated by using this expression, summation over S, ES, PS. So E1, P1 plus E2, P2 plus E3, P3. So a substitute for E1 is equal to 0. So the first time is 0 into P1. The second time is E2 is E, therefore E into e power minus beta E by Z. E3 is 2E. P3 we have already evaluated e power minus beta E by Z. So once if you add all the three terms and if you find substitute for Z, you will get this is this final expression. So this is the mean energy. So option C is the correct one. E power minus beta E plus 2E e power minus 2 beta E whole divided by 1 plus e power minus beta E plus e power minus 2 beta E. So if a problem is a boson, so we must be careful. Now let us do some problems using degenerate levels. So far we have discussed problems using non-degenerate levels. Now let us use apply this problem, apply this formula for finding the average energy for degeneracy levels. Now you take a problem. Consider a system of n particles distributed in various energy levels with energy E, 2E and 3E, and the degeneracy of the levels are respectively 1, 2 and 3. Find the mean energy of the system at temperature T with beta is equal to 1 by K. So now here first energy is energy E and the degeneracy is given as 1. Second level is energy 2E and the degeneracy is 2. and the third level is energy 3E with degeneracy. So in that case, what is the expression for Z? Z is equal to summation over S. So the multiplicity of the level GS, which is included in this formula. So summation over S, GS e power minus beta S. So once if you expand this summation, the first term will be G1 e power minus beta E1. G1 is equal to 1 and E1 is equal to E. So this is first term. Second term, GS is equal to the multiplicity of the level is 2 and E2 is 2E. So this is your second term. And third term is the multiplicity of the level is 3 and the energy is 3E. So you substitute, you will get the partition function e power minus beta E plus 2 e power minus 2 beta E plus 3 e power minus 3 beta E. Then let us calculate the expression for PS. Calculate the probability of occupation. So P suffix x is equal to, again you have the expression GS is e power minus beta ES divided by Z. So using this expression, you substitute P1, find P1. P1 is equal to G1 is equal to 1, e power minus beta E1 is equal to E divided by Z. Similarly, P2 is equal to G2 is equal to 2, and here the energy is 2E. So 2 into e power minus 2 beta E divided by Z. P3, G3 is equal to 3 and e power minus 3 beta E divided by Z, because E3 is equal to 3E. So P1, P2, P3 is now evaluated. Now from this, the mean energy can be calculated. Mean energy is summation over S, PS, ES. So E1, P1 plus E2, P2 plus E3, P3. We already calculated P1, P2, P3. You know the expression for E1, E2, E3. E1 is equal to 2E, E1 is equal to E, E2 is equal to 2E, E3 is equal to 3E. And you know you have already calculated P1, P2, P3. So once if you substitute this expression, it becomes like this. This is the expression. Now you substitute for the partition function Z, and the expression of the final expression becomes e power minus beta E plus 4E e power minus 2 beta E plus 9E e power minus 3 beta E whole divided by e power minus beta E plus 2 e power minus 2 beta E plus 3 e power minus 3 beta E. So this is the mean energy. So for degenerate system, you have to use a slightly different formula so that you can calculate the mean energy of the system. Now you take another problem, the problem number 4. Consider a system whose energy levels are 0, E and 2E. The energy levels E is W degenerate and the other levels are non-degenerate. Find the partition function, also find the energy of the system. So here the second level is degenerate, other levels are non-degenerate. So in that case, now, so here the multiplicity is 1, here multiplicity is 1, this is the value of G here, this is G. Whereas here the multiplicity is 2, that is important. So now the expression for Z is equal to the summation over S, G suffix S e power minus beta epsilon S. So here the first the multiplicity is 1, first level, G1 is 1, e power minus beta, the energy is 0, which is also given. For the second term, G2 is 2 and the energy is E, so e power minus beta E. And the third level is also non-degenerate, so G3 is equal to 1 e power minus 2 beta times 2E. So is that the partition function is now evaluated. Then let us calculate the probability. So PS is equal to, you have to use the expression GS e power minus beta ES whole divided by Z. So from this let us first calculate P1. For P1 G, here you have to use G1, multiplicity of the level is 1. So 1 into e power minus beta into 0 whole divided by Z. And the second term is, let us calculate the P2, which is G2 is equal to 2 and the energy is E. So 2 e power beta E divided by Z, and P3 is equal to 1 into e power minus beta 2E whole divided by Z. So P1, P2, P3. Then the mean energy can be found by using the expression summation over S, ES, PS. So E1 is equal to 0, and this is P1 by Z, because this is P1. PO, so actually this is here you should not use Z here, because E1 P1 plus E2 P2 plus E3 P3. So once if you use P2 is equal to 2 e power minus beta E whole divided by Z. Now here you can use this. Yes. For the first term, since it is 0, the term Z will not appear, because the expression for P1 is equal to 1 into e power minus beta 0 divided by E. Okay, now we substitute for E1, P1 in the expression for Z. This is the mean energy, and the expression for mean energy this can be evaluated. So Z is a common value. You take the average. Z is a common factor. 1 plus e power 1 plus 2 e power minus beta E plus e power minus 2 beta E is that we have already determined, which is in the denominator, and the numerator becomes 2e e power minus beta E plus 2e e power minus 2 beta E. So this is the expression for the mean energy of the system. Then let us go to the next problem. Problem 6. Consider a system whose energy levels are 3 by 2 h cross omega, 5 by 2 h cross omega, with the degeneracies 1 and 3 respectively. So here G1 is equal to 1, non-degenerate level, and the next level is the degeneracy is 3, G is equal to 3. The energies for the lower level is 3 by 2 h cross omega, the upper level is 5 by 2 h cross omega. Now let us calculate the partition function first. So let us use this expression. Here G1 is equal to 1, therefore E1 is equal to 3 by 2 h cross omega, G2 is equal to 3, and E2 is equal to 5 by 2 h cross omega. So this is the expression for Z. Then let us calculate P1, P2. So using the expression for PS, you substitute, if you want to find P1, you have to find G1 is equal to 1, and E1 is equal to 3 by 2 h cross omega. Similarly for P2, this is G2 is equal to 3, and E2 is equal to 5 by 2 h cross omega. So you substitute for so you can find P1 and P2. Now let us evaluate the mean energy of the system, which is U, the expression for the mean energy and the average energy of the system is U is equal to summation over S. This is summation over S, ES, PS, which is equal to here you substitute for ES, the first one is 3 by 2, this is 3 by 2 h cross omega into, you substitute for P1, and 5 by plus 5 by 2 h cross omega into P2, and once if you simplify, you will get this expression. This is the expression, the average. So the 3 by 2 h cross omega is a common factor. If we take outside, this is a e power minus 3 by 2 beta h cross omega plus 5 e power minus 5 by 2 beta h cross omega. This is the numerator, and the denominator e power minus 3 by 2 beta h cross omega plus 3 e power minus 5 by 2 beta h cross omega. Now the next problem. N particles are distributed among two states. E is equal to 0 and E is equal to kBt. The probability of occupation of energy E is equal to 0 at temperature T is given by. So there are 4 options are given. Now here the energies are the first level. So this is a 0 is the energy corresponding to the first level. kBt is the energy corresponding to the second level, and this is a non-degenerate level. So the expression for the partition function is like this. So there is a G suffix x is 1 because there is a non-degenerate level. Now you expand the summation for the first state. The energy is 0, so E power 0. The second one is this kBt, so this is e power minus beta kBt. So this becomes 1 plus e power minus beta kBt, and beta is already we know, which is 1 by kBt. So substitute for beta is 1 by kBt. So this expression becomes 1 plus e power minus 1 or 1 plus 1 by e, and if we take e is a common factor, it becomes e plus 1 divided by e. Now let us calculate PS. So this expression of PS, you are asked to find P1 because the probability of occupation of energy E is equal to 0. So you have to find P. Probability of occupation of energy E is equal to 0. So you are asked to find P1 alone. So e power minus beta, the energy is 0. So you substitute here divided by Z, which is 1 by Z, and we have already calculated the partition function. You substitute this value here and you simplify. This becomes E divided by E plus 1. So this is your option 1 is the correct one. So this is the correct option. Then the next question is question number 8. A system has two energy levels, where the energy is E and 2E. The lower level is fourfold degenerate, and the upper level is doubly degenerate. If there are n non-interacting classical particles in the system, which is in thermodynamic equilibrium at a temperature T, the fractional particle in the upper level is. So the 4 options are given. So here the first level degeneracy is 4, and this is the energy is E. Here second level is 2E, and the degeneracy is 2. So the expression for the partition function is Z is equal to summation over S Gs e power of beta S, and Gs is for the first level, this multiplicity is 4, so Gs 1 is equal to 4, and the E suffix as E1 is equal to E. So this is your first term, 4 e power minus beta E, and the second term Gs is equal to 2, and the energy is 2E, and therefore this is the expression for the partition function. Now you know the next one is you have to find the PS. For P here, the question is the fractional particle in the upper level. So you are asked to find the P2. So you have to find P2. To find the P2 is equal to Gs is equal to 2 e power minus beta 2e divided by Z. You substitute for Z here. Then if you simplifying, you will get 1 divided by 1 plus uh, 2 e power beta e. So the option 2 is correct option. So you are asked to find P2. The next question is question number 9. There are more than two systems A, B, C and so on, which are almost independent of each other. Suppose that they interact with each other weakly, so that they can be regarded as a compound system A plus B plus C and so on. The partition function and free energy of the systems are given by. So there are 4 options are given. The partition function gets multiplied. The overall partition function Z is equal to given by Z suffix A, Z suffix B into Z suffix C and so on. So you have to multiply the partition function to get the overall partition function, and the energy must be added. So this is here it is multiplied, the energy must be added. So this is F is equal to F suffix A plus F suffix B plus F suffix C and so on. So the partition function must be multiplied and the energy must be added. That is more important. So this is the answer 3 is a correct answer. Then question number 10. The system has a fixed number of particles n. Suppose the energy scale is shifted by an arbitrary constant eta. The new and old partition function Z prime and Z will be related as here again there are 4 options are given. So the solution is, see, the first one is having energy E. So here this is E and it is shifted by eta. So this is E plus eta. So for the new system, Z prime is equal to E power minus beta ES. ES is equal to E plus eta for n particles. So for n particles you have to multiply by n. So for before shifting the old partition, let us use the old partition function. Then Z is equal to summation over S e power minus beta ES. Here it is the energy is E. So the new system is having energy E plus eta. The old system is having energy E. So the partition function is here. This is Z. Z is equal to E power minus beta E n for n particles is n. So this Z prime by Z can be calculated. E power minus beta E plus eta into n divided by E power minus beta E into n. By simplifying, you will get this expression E power minus beta eta into n. So this option 3 is the correct one. So this is the correct one. The next problem is a large isolated system of n weakly interacting particles is in thermal equilibrium. Each particle has only 3 possible non-degenerate states of energy 0, E, 3E when the system is at absolute temperature T, which is greater than E by K, where K is a Boltzmann constant. The average energy of the system. So there are 4 options are given. So here the first one is energy 0, E, 3, and this is non-degenerate systems. Therefore, the multiplicity of the levels are 1. So you have to use the expression for Z. Z is equal to summation over S, e power minus beta E surface x. So E1 is equal to 0, E2 is equal to E2 is equal to E, and E3 is equal to 3E. So the partition function will be 1 plus e power minus beta E plus e power minus 3 beta E. Now let us evaluate P1, P2, P3. So using this expression of PS, P1 is equal to e power minus beta into E0 divided by Z. E0 is E1 divided by Z. E1 is equal to 0. So you will get this expression. So which is 1 by Z. The next case e power minus beta E divided by Z, and the second case e power minus 3 minus beta into here the E3 is equal to 3E. So this is your P3. So P1, P2, P3 become evaluated. Then the average energy this is expressed for average energy. This is summation over S, ES, PS. So S is equal to 0 into P1, E into P2, and 3 into P3. Substitute for P2 and P3, and you will get this expression. And if you simplify, substitute for Z, you will get this expression becomes like this. So this is the expression. Here the temperature T must be greater than E by K. So E by KT tends to 0 because the temperature is very large. So e power minus E by KT tends to 1 when T is very large. So the exponential factor must be 1. E power minus E by KT or E power minus 3 by KT is 1. Therefore, this expression now becomes U is equal to E into 1 plus 3E into 1 whole divided by here this is 1 plus 1 plus 1, 1 plus 1 plus 1. So this is 3. So 4E by 3. So this is your correct option. So 4E divided by 3 is a correct value. The average is right. Now let us go to the next problem. Question number 11. This is question number 11. Now consider a collection of n two-level systems in thermal equilibrium at temperature T. Each system has only 2 states, a ground state of energy 0 and an excited state of energy E. The probability that the given system will be in the excited state is. So here there are 2 levels. One is having energy 0, another is having energy E. So now let us calculate P suffix x. This is the expression for PS, probability, e power minus beta Es divided by Z. Z is equal to summation over S, e power minus beta Es. Since you have 2 levels, E lower level is 0, the upper level is E. So this is the expression for Z, 1 plus e power minus beta E. You are asked to find P2. So for P2, then this is equal to e power e power minus beta e divided by z, and z we have already found 1 plus e power minus beta e, and therefore e power minus beta e divided by 1 plus e power minus beta e, and if we take the e power minus beta e from the numerator to the denominator, that expression is reduced to 1 plus 1 divided by 1 plus e power beta e. So the option 3 is the correct answer. Then we will go to the next problem. A system has two energy levels of energies 0 and E with the degeneracies 1 and 3 respectively. Calculate the temperature at which the possibility of finding the system in the lower level is equal to half. Now here it is given the lower level is energy 0, the upper level is energy E, but the degeneracies for lower level is 1 and the upper level is this is given. So Z can be easily found by using this expression. Here G1 is equal to 1 and G2 is equal to 3. Therefore the expression for Z now becomes this form. This is 1 plus 3 e power minus beta E. Then the expression for PS is GS e power minus beta ES divided by Z. So you can find P1 here, G1 e power minus beta, and the energy is 0, plus P2 is equal to G2 e power minus beta, here the energy is E. Now the value of P1, the value of P1 is simplified to, so this is 1 divided by 1 plus 3 e power minus beta E. So it is given, the probability is equal to half. This is here, this is given. So you simplify this expression, 1 plus 3 e power minus beta E is equal to 2. So if you simplify 3 e power minus beta E is equal to 1, or e power minus beta is equal to 1 by 3, or beta E is equal to, you take log on both sides, e power minus beta E is equal to logarithm of 1 by 3, or beta is equal to logarithm of 3, or beta, you substitute for beta, beta is equal to here beta is 1 by kt, so 1 by kt into E is equal to logarithm of 3, you simplify, t is equal to E divided by k logarithm of 3. So the option 4 is the correct answer. So this is your correct answer. We take the next problem. Question number 13. Consider a system of n particles with only 3 possible energy levels separated by energies 0, E, 2E. The system occupies a fixed volume V and is in thermal equilibrium with a reservoir at a temperature T. The average energy of the system is, because occupies a fixed volume, so it's a canonical system. The temperature T is also remains constant, so it's a canonical system. So here are 4 options are given. Now let us find the correct value. So energy is 0, E and 2E. So the expression for Z is like this, because non-degenerate system. So the expression e power minus beta, the energy is 0. For the second term, e power minus beta, E2 is E, and here this is 2E. So once if we substitute, we can find the value of Z. Then next step is you have to calculate the P1, P2 and P3. This is the expression of Ps. So find P1, which is 1 by Z. Find P2, which is e power minus beta e divided by Z. Find P3, this is e power minus 2 beta e by Z. So the average energy and our mean energy is given by U is equal to summation over here CS PS. So E1 is 0, 0 into P1. This is E2, E3, and substitute for E2 and P2, E3 and P3 here, and if you simplify, you get this expression. So the simplified expression is this, which is the option 1 is the correct one. E into e power minus beta e plus 2 e power minus 2 beta e whole divided by 1 plus e power minus beta e plus e power minus 2 beta e. Now what is the probability that the 2E level is occupied in the higher temperature limit? KT is greater than V. So this is the second part of this problem. Now the expression for this is the P3, because this is 2E is third level P3. So P3 you have to calculate e power minus beta into E3 is equal to 2E, so minus e power minus 2 beta e whole divided by Z. So this is the expression for it. When Kt is greater than E, so what is e power minus beta e? So beta e must be reduced to 1, because beta is 1 by Kt. T is Kt is very larger, so e power minus beta e tends to that factor, and beta e tends to 0. Therefore, this is must be 1. So e power minus beta e is also 1. So once if we substitute, this value P3 becomes 1 by 3. So this may be calculated. The next problem. Consider a system of n weakly interacting atoms, each of which can be in either of two states with respect to energies E1 and E2, where E1 is less than E2. And the mean energy of the system is given by. So there are 4 options are given. So this is E1. Another level is E2. So Z is equal to the expression summation over here e power minus beta ES. Then this can be, if you expand the summation, this e power minus beta E1 plus e power minus beta E2. So find the P1, P2 also. So the expression of P1 is e power minus beta E1 by Z, and the expression for P2 is equal to e power minus beta E2 divided by Z. So you know P1, P2. Now from this you can find the expression for U. U is equal to summation over S, ES, PS, E1, P1 plus E2, P2. So substitute for E1, we have already evaluated P1. So you substitute here for P1 here, for P2 here, and Z is a common value, so you take Z is a common factor that we already evaluated. So this expression becomes like this. So 8 power minus beta e, if you take as a common factor, then this expression becomes, we simplify to U is equal to E plus E2 e power minus beta into E2 minus E1 whole divided by e power minus beta E2 minus E1, and substitute for beta, this beta is 1 by Kt. Therefore, the expression for E becomes E1 plus E2 e power minus of E2 minus E1 whole divided by Kt whole divided by 1 plus e power minus E2 by E1 by Kt. So option 4 is the correct option. Next problem, question number 15. A particle is in thermal equilibrium which has 3 possible states of the energy minus E, 0, E. If the system is maintained at temperature T greater than E by Kt, the average energy of the particle can be approximated to. So in this problem, so the energy levels are minus E, 0, E. So now Z can be calculated by using this expression for ES. So the first level is 0 minus E, so this becomes E power beta E. Second term is E power 0, and third term is E power minus beta E. So the Z value is 1 plus E power beta E plus E power minus beta E. That is the expression for the partition function. Then let us evaluate the probability. So first evaluate P1, P2 and P3. So these are the expression for P1, P2, P3. Then the energy U is equal to summation over S, ES, PS. We substitute for ES, the lower value. First one is minus E, E power minus beta E by Z. Second time is 0 into P2. And the third level is plus E in the E power minus beta E by Z. So if you this is equal to now here let us take this expression for E power beta E. This is E power E by KT, and KT is larger, so this is a exponential E by KT is smaller, so that can be expanded in series. So we keeping the first term itself is very small when compared with 1, so the higher order terms can be removed. So 1 plus E by KT. Similarly for E power minus beta E also, the 1 minus E by KT, the higher order terms can be removed because this is very small when compared with the second term. So for when T is greater than E by KT, the exponential factor of E power K by T, E power E divided by KT, and E power minus E by KT can be expanded, keeping retaining the first order, the higher order terms can be removed. Therefore, the average energy you substitute for the exponential values in that expression, and U becomes like this. So this is the expression for U, and once if we simplify this expression, the simplified expression is minus 2 E square by E square divided by KT by 3. So this is the expression for your the expression for now U now is equal to this expression. Actually this is 2. So minus 2 by 3 E square by KT. And the next problem is a two-level system has energy 0 and E. The level with the 0 energy is non-degenerate, while the level E is triply degenerate. The mean energy of the classical particle in the system at temperature is. So here you choose a two-level system, and here the lower level is and the multiplicity is 1. For the higher level, the multiplicity is 3. Then using the expression, you can calculate the value of Z. Here this is the partition function. This can be evaluated as 1 plus 3 E power minus beta E. And PS, the probability, and that can be also evaluated. PS is equal to GS E power minus beta E PS by Z. P1 the degeneration is 1, so this is the first term, which is equal to 1 by Z. For P2, G2 is equal to 3, and the energy is E. So using P1, P2 and Z, and the expression for Z, U, the average energy is evaluated using this expression. 0 times P1 plus E times P2. The substitute for P1 P2 will do this expression. So 3E e power with beta E divided by 1 plus 3 e power with beta E. Now we are so far we have discussed so many different types of problems which were previously asked in your NEET GATE examinations. So this is the way you can calculate the internal energy of the system for the if the system is a canonical result. Thank you.